This is Unit 2, Lecture 2, where we are going to continue our talk about strain on rocks. And remember, a strain on a rock is a permanent change due to a stress. And the stresses arrives from the moving tectonic plates that we talked about in Unit 1. So the first type of strain we're going to talk about is a type of strain called a fold. And a fold is a ductile type of strain. That means it just has bending and twisting, but there's no breaking in the rock. And so in a fold, the rocks get bent. And most of the time, we see folds come in through a compression strain, which is also usually at convergent boundaries. So convergent boundaries, where the plates are being squished together, where they're colliding, generally results in compression stress, which can lead for rocks to fold. Like if you started pushing the ends of two sides of your paper together, you would see that paper fold, and it would either fold up or it would fold down in the middle. And so in a fold, what we see is normally we would have flat layers of rock called strata. Well, instead of seeing nice straight horizontal strata, as we would see right here in these lines, this is normal. In a fold, and I'll switch colors here, we see where they look like they've been pushed or smushed together and folded up. Or sometimes they can fold, a rock can fold down. So the big thing is we see these layers of rock where the rock gets compressed, squeezed inside, and while we normally find them from compression, we can also see folds coming from shear stress, and those are from those transform boundaries where the plates are sliding past each other. Now when we look at a fold, there are different parts, and you can see in the picture over here what those different parts are. There's an axial plane, and that cuts right down the middle of the fold and breaks it into two symmetrical halves. That means if you look at that plane, one side of the plane is a mirror image of the other side of a plane. Now that plane runs right through the center of the fold, which is kind of like the turning point, which is known as the hinge. And each of the two sides of the fold are known as the limbs, kind of like your legs are the limbs. The hinge would be your pelvic area, and the axial plane would go right through it. Now sometimes the fold is overturned and it's lying on its side, and so the axial plane is horizontal. Or it could be partially turned and the axial plane could be diagonal. The big thing is to find the axial plane. You need to find where the two symmetrical halves are, and you're going to look for that general folding, the general folding shape like we see right here. There are three types of folds, and each type tells us something different about the age of the rocks inside. So one of the things we do when we look at a fold is we look at the relative ages of rocks. By relative ages, this involves no numbers. We're just trying to figure out what rock is older, what rock is younger. We don't know how much older, we don't know how much younger. It's like if we looked at the high school, the seniors are older than the sophomores, and the sophomores are older than you guys. Those are relative ages. We don't know the exact number of days. We're not even going into the exact number of years. We just know that seniors are older than sophomores, sophomores are older than freshmen, freshmen are older than 7th graders, and so on. So the first of these is called an anticline. And at an anticline, the oldest rock is right in the center of the fold. It's in the middle. Alright, they look like arches. Alright, they're shaped almost like little N's. And the old rock is in the middle, and the new rock was on top of it. So the oldest layer is in the center of the fold. Alright, and again, arch-shaped is the big thing. Here's our forces, our compression force coming in, squeezing the rocks together. And so the layer that would have been normal and straight on the bottom is now, this layer right here that would have been straight on the bottom, is now in the center of our fold. The next type of fold is a syncline. And a syncline is the opposite of a anticline, and it makes a U-shaped or a bowl-shaped. And in an anticline, the oldest rock was in the center of the fold. In a syncline, the youngest rock is in the center of the fold. So this is like if you had your piece of paper and you kind of held it to get out and squeezed both ends. This would be the paper folding down instead of up, making that valley shape, that bowl shape. The final type of fold is the monocline, and they're a little harder to see. They make almost an S shape instead of an arch or a bowl, an N or a U. And what happens here is the crust of one part moves up or down compared to the other. So both limbs are horizontal instead of vertical. In the syncline, which I'll do in purple here, the syncline is a U shape. The limbs are horizontal right here. Right here, here are the limbs. Alright. In an anticline is an N shape, like this right here. And again, here are the limbs, right here and right here, and they are vertical. In the monocline, your limbs are horizontal to each other, and then there's like a little bend between them. It's almost an S shape, so you get more of a step-like structure than you get a bowl or a arch. They are step-like. Alright, and again, the force causing this is one of the sides is moving up compared to the other side. Folds themselves can sometimes be really small. You can go in your backyard, dig down a little ways, see some rocks, or be walking out in the woods, see some rocks, and you can get a rock, hold it in your hand, and you can see it. You can see folds in a small rock specimen. Alright, so they can be tiny and within a single rock, or they can cover thousands of square kilometers. Alright, same as thousands of square miles. 1 kilometer equals about 0.6 miles. Alright, and so we can only see them from the air. If we have one of these really big, long anticlines, we might see a ridge, a long hill line almost, and a very narrow strip of elevated land. A lot of times we can see this near mountains, especially mountains that are forming where two plates are colliding, like the Himalaya Mountains. That the Himalaya Mountains have been formed because India has collided with Asia, and India was or is a little bit denser. The crust of India is a little denser than the crust of Asia, so it subducted and pushed up the Himalaya Mountains, and the Himalaya Mountains are still growing every year, I think by about a quarter of an inch. Well, if an anticline makes a ridge, a large syncline could form a valley. And remember, this is again where it's pushing down instead of up. Syncline goes down, anticline goes up. All right, and those are the main types of ductile strain are the folds. The main type of brittle strain, and I am pretty sure you've heard this before, is called a fault. And a fault is a break in a rock. Sometimes it's called a crack in a rock. Sometimes it's called a fracture in the rock. Some type of fracture, break, crack, and we call this brittle strain. Now, usually fracture refers to when there is no movement of the surrounding rock. The rock just breaks. Alright, you get a crack that goes through it, and nothing big happens. If we have one of these breaks, one of these cracks, and then the surrounding rock moves, the way that surrounding rock moves gives us a fault. And there are different types of faults depending on how the rocks move. So, the place where the crack occurs, or where the motion occurs, is called the fault plane. Alright, that's where that motion is occurring. And we'll see examples of all these on the next slides. In a fault that's not vertical, so not straight up and down, usually what we're talking about here, when we're talking about non-vertical, we're talking about diagonal. Alright, we got a diagonal fault. So if this is our big block of rock, here is our fault right here. Alright, so the rocks that are above the fault plane are the hanging wall, the rocks that are below the fault plane are the footwall. And as we see examples of the different faults, I'm going to point out the footwall and the hanging wall to you so that we can see how you could have two faults, but it all depends on where the rocks have moved. So the first thing is we're looking at a normal fault. In a normal fault, the hanging wall goes down. Now, in order to see that, the first thing you have to find where that fault is. Find where the fault is, where the fault plane is. In most cases, it's right where the movement occurred. So in this case, it is right here at this red line. Alright, and then if we look at it, this rock over here is kind of above the fault. If we looked at the fault, you can see it's diagonal. Alright, but it is on the more upper half of the diagonal line. The other one's more below the diagonal line. That's why we're talking about non-vertical. If it was straight up and down, there'd be the left side and the right side. Since this is not straight up and down, it's diagonal, this is a little bit more on the top side of the line than the bottom. So footwall's on the bottom side of the line, hanging wall's on the top side of the line. And what we have here is we have this hanging wall has moved down compared to the footwall. Alright, so the hanging wall went down, the footwall went up. And when we have a case such as this, we get steep, step-like landforms. So Yeah, I've used step-like before to talk about the monoclines. The big difference is you're seeing a crack in the wall. You're seeing. I'm going to erase the red marker here. I guess I can't. You're seeing this crack in the rocks. All right, you don't see any bending. This, let's say, dark band of rock here went over, and then this side moved down and it goes over here. It doesn't have that nice smooth S shape that you would expect from a fold. There's this crack, this break right in the way. Opposite of the normal fault is the reverse fault, which the reverse happens. So if in a normal fault the hanging wall moved down compared to the footwall, in a reverse fault the hanging wall moves upward. Alright, again, here's the crack right here. This is the hanging wall. Here's the footwall. There's the fault plane. Right in there. The hanging wall moved up. There's a special type of fault, reverse fault, called a thrust fault. And this just means that we have a very low angle breakage, a very low angle fault plane. It's almost horizontal instead of almost vertical. And now it looks like the one slid upon on top of the other, but you're just looking for this horizontal, and the top part of this is the hanging, the bottom is the foot. And we see these type of faults more at colliding boundaries, more at those convergent boundaries. And the Rockies and the Alps are examples of mountains that have a lot of reverse faults and thrust faults in them. They tend to be very steep, jagged-looking mountain ranges. The third type of fault is probably the one you think of the most, and that's a strike-slip fault. And what happens is as the two plates slide past each other, they sometimes slip right past each other. Other times they strike each other, causing a release of energy. And this happens to shear stress. Alright, and these are common at transform boundaries, right here. And at these transform boundaries, we see a lot of these strike-slip faults. So the fault in this case, the break is right here. Alright, so if I was to label hanging and foot walls here, here's the hanging wall, here's the foot wall. Right here, this red line, that's the crack. But what we're seeing is the motion we are seeing. The motion we are seeing is horizontal. It is in a different direction. Alright, so in a normal fault, the hanging wall went down. In a reverse fault, the hanging wall went up. Strike-slip fault, they're going side to side. Faults, just like folds can be big or they can be small. Again, you can see faults that affect just a very small range of rocks, a small little region. Or you can have other faults that are several thousand kilometers long. The most common or the most studied fault, and probably the most well known to you guys, is the San Andreas Fault, which runs through California. Alright, it covers most of the state of California. Here's San Francisco, San Jose right here. Los Angeles is down here, so it doesn't go through Los Angeles, but it does go through San Fran. And this is the fault right here that most of the earthquakes that hit Southern California and even mid-California, where San Fran is, this is the fault line where those earthquakes are occurring. And because it's a long strike-slip fault, what we end up with we can end up with several earthquakes along it as the two plates slide and hit each other. Now, really, this is called the San Andreas Fault, and it can go down underneath the surface for several thousand kilometers. There's actually a very old fault that runs through Oklahoma and kind of the Mississippi Valley, where the Mississippi River is, and so once in a while we see earthquakes in those areas, and they were areas of a very old ancient fault line. There's a lot more rock on top of them now that has been deposited there, so once in a while we see an earthquake in the center of a continent in the mainland U.S. where there shouldn't be a lot of tectonic movement because it's all part of the North American plate, but there's a very old fault line deep underground, and sometimes the rocks shift. And we've actually seen a slight increase, it appears, in those areas as we remove stuff from the rocks. And as you take something out, you're taking out support. Like if you were to dig down under the ground and then dig a hole across, you're kind of counting on the rock or the rocks or the dirt around you to support the ground above it. Sometimes that ground gets too heavy and we have a break in the rock, and then we have an earthquake. And the next video lecture is all about earthquakes. Anyway, back to these large faults like the San Andreas Fault. The San Andreas Fault, way below Earth's surface, thousands of kilometers long, going across the entire state of California, but really if we look at it, it is a collection of many smaller related faults. They run into each other. It's not a beautiful straight line. You guys saw the picture during the WebQuest in the last unit, and that's part of the fault, especially down in this area. But you can't go to San Fran in the downtown part of the city and see part of the fault. Alright, it kind of goes underground a little bit here. It's a little bit away from the city. But there's a bunch of little smaller systems that are all connected to each other, all caused by the same plate movement. Here we got the North American plate moving. Here's, I believe, the Pacific plate moving, and they're sliding and grinding past each other. And every time they hit each other, a little bit of rock might get ripped off, causing a break, which is a fault, and that releases energy into the earth, and we get an earthquake. As I said, our next video is going to be on earthquakes. If you have any questions, please feel free to bring them up in your next class, and have a good night.